Hello, in this lecture, we are going to discuss doubt resolution. I'm going to resolve a doubt, which was actually raised by Bharat, and actually he wanted to explain me the solution for the Laplace's equation, spherical polar coordinates, specifically the problem of conducting sphere in a uniform electric field. Okay, I hope I feel that there is some discrepancy in the uh, lectures previously done. So I'm going to resolve that discrepancy, and I hope everybody would get uh, what is the discrepancy and what is the ambiguity. Okay, so just give me a minute. Okay, so so we've already discussed this particular problem, but however, there is certain like there was an issue which I wanted to resolve, and I hope that I'll resolve this entire problem. And once I resolve this entire problem, you will be able to figure out what the issue was and how that can be resolved. Okay, so I discussed in the lecture the classical problem of conducting sphere in a in a in a uniform electric field in a uniform electric field. Okay, this is what we were discussing in one of the lectures. And in those lectures, somewhere I made a slight mistake, or you can say that there was a discrepancy in solution. And that is what I'm trying to resolve here. Okay, so let us consider the case of a conducting sphere. So I took a conducting sphere and we placed it in an external electric field, E naught k cap. So we place this particular sphere in an external electric field E naught k cap. And we wanted to find what is the potential in general. We wanted to find what is the potential in general outside. Outside the sphere. Okay. Now there are a few boundary conditions that one needs to understand. Since this is a conductor, the electric lines of force would enter normally and leave normally. Electric lines of force would enter normally on the surface and leave normally from the surface. So this is the first thing that one needs to keep in mind, because we are studying electrostatics, and if had it not been perpendicular, then some component would get resolved along the surface and charges would be in motion. And also one can understand that because of the electric field, there would be some induced charges on the inner surface. I hope this is clear. Now, the first condition that one needs to understand here is that no longer I can write my potential outside as this form. No longer I can write in this form. Why? Because you can see that as r tends to infinity also, there is some electric field, because this electric field extends to infinity. This electric field extends to infinity. And second thing one needs to understand that on the conducting sphere, the potential would be a constant. Conducting sphere, on the conducting sphere, the potential would be some constant, because the surface of a conductor is an equipotential. Surface must be a constant. So this is what we took. Although I uploaded one other lecture called as Griffith's approach, in that approach, Griffith has taken potential to be 0. So I'm not taking it as 0. I'm taking it as general as phi naught here. Okay. So now let us solve this particular problem given these two conditions. Okay. The first thing that comes in mind is that since your electric field is extending all over till infinity, so I'll write it as E naught k cap, and I know that my potential in general would be like this form. And I can write your V as a function of Z, that is minus E naught Z plus C. Okay, is that clear? Now, further as you move along, you can see that your potential, if expressed in R and theta, can be written as E naught minus E naught R cos theta plus C. And you can see that yes, as your R tends to infinity, your potential is no longer tending to 0, rather it is tending to infinity only. So no longer can you write that this is the only way to express your potential outside. So in general, I'll write potential would be equals to summation L equals to 0 to infinity. I'll write AL R raised to power L plus BL upon R raised to power L plus 1. And then I will write PL cos theta. And as I know, for very far off condition, that is for all R greater than R, or I can say as R tends to infinite also, my potential would remain as minus E naught R, and I would write it as cos theta plus C. This is how it will remain. Okay, but overall understand, as r tends to infinite, this particular term would go to zero. Only term that survives is this, and you can clearly see that your a naught in that case would be equals to C. Your a1 in that case would be equals to minus e naught, because you see a naught is like constant. A naught is r to the power 0, is that a naught is a constant here is C, and a1 would be accompany r and some cos theta term. So if you compare that up, you will get a1 as minus a naught and a naught as C. I hope it is clear. So one can understand that in general, till now, whatever conditions has been supplied to me, also understand I have not written this term uh, as like I have not written BLs as 0. I have written, since r tends to infinity, this term would go to 0. Okay, this term would go to 0. So in general, I can write my potential. Achha, another thing that one needs to understand is, will there be B0 term? Will there be B0 term? So one needs to understand that the problem that we are discussing contains no sources within, no sinks within. That is, there are no source term within, or neither you can find anywhere the there is no such charges present. These charges are induced charges. Understand, there are no source charges. So basically, this particular problem satisfies the condition for the Laplace's equation. That is, there are no sources within as well as outside. So now focus yourself on B naught. Will there be some term B naught? So I will think opposite. So if B naught was there, let us think that if B naught was there, forget about initial terms. There would be some terms in N's, L's, and all those things. But if certain term B naught exists, that implies there would be a term of this in this fashion. See, if you write B naught, so B naught upon R and P naught is 1. So I'm just writing these terms would be there, but there would be this term as well. If this term happens to be there, I have already taught you that your del square 1 upon R is given by minus 4 pi Dirac cube of R. Okay, this is what we have already discussed in our Errata function. All those who have not seen this lecture, kindly see this lecture. So if this term remains, then if I just try to take the Laplacian of P, which is my initial equation, like this is my initial equation, isn't it? By these, what we are solving only Laplacian equation, isn't it? So if I take del square V, so there would be some del square of these bracketed terms. I'm not concerned about this, but this will also be there. And having this term means you're having some point charge at r equal to 0. It implies what? It implies that there is some source within. It signifies that there is some source within. But we know that there is no such source. Del square 1 upon r means that there is a point charge or some point charge kind of thing at the center, that is at r equal to 0, which is not the case. So clearly B naught would not be there. B naught will not be there, since its presence would lead to understanding that there is some source term. There is some source within, which is not the case. We know that we are considering that del square B is equal to 0. That is, there is no source within as well as outside. So one needs to understand there would be no BL. So there will be no 0 term in expansions of BLs as well. So what I will get in general, I can write my V as a function of r comma theta as a naught, like C minus a1, that is e naught, and I can write r cos theta, and then I will write summation L equal to 1 to infinity BL upon r raised to power L plus 1, and then I'll write PL cos theta. Now, also one needs to see that that the surface of the surface of the conducting sphere is an EQ potential, and that EQ potential is equals to phi naught. So if I write V r comma theta and I compare it with phi naught, what I will get? Okay, what I will get? So I will simply get C is equal to phi naught. Okay, and then I will also get C. I'll expand this entire thing up, and then I'll be able to understand. So I'll do one thing. So C would be phi naught, because see here, if you write C minus E naught r cos theta, B naught is not there, so I'll write B1 upon r square, and this P1 is again cos theta, and then there would be some higher order terms in BL, B2 upon r cube, there would be 3 cos square theta minus 1 upon 2, and so on and so forth. And all these things would be equated to phi naught. One can clearly see that constant is phi naught. So C happens to be phi naught. Okay. Now remaining term, this cos theta dependent term here, there is no such cos theta dependent term. So I will write that E naught minus E naught R plus B1 upon R square would be 0, since there is no term on right hand side, no term in our right hand side in cos theta. Since there is no term in right hand side in cos theta, this would be it. So it implies your B1 would be equals to what? It will be equals to minus E naught R cube. And all other BLs would be 0, because all these terms, there are no cos square term and all those things are not there. So one can say that your all other BL would be 0, except L equals to 1. Because at L equals to 1, there will be some value. So overall, one can clearly write the potential as, phi naught minus E naught R cos theta. And then one can write minus, I think this will be minus, if I'm not wrong, this will be like, sorry, this will not be minus, this will be plus only because it goes there. So it will be like plus E naught upon R cube divided by, I think there would be some, because there is B1, so there will be R square cos theta. And that day also I told you that this term, it was because of the net external field outside. This term is because of the induced charge distribution within the sphere. So this term is the modification that has been brought about by modified because of the presence of induced charges. So in that particular lecture that I taught you, actually I disregarded these constant values, and which gave the discrepancy which one student happens to see. And so therefore I have resolved this entire problem. The source of the problem is here. One needs to figure out that this B naught will not exist. And once this is clear, I think there would be no such discrepancy in that particular lecture. All other things can be followed from here. So I hope I have solved this doubt. Kindly help yourself with this solution, and kindly let me know if there is some discrepancy still there. Okay. So thank you very much.